Imagine a scene. In front of you are three slot machines. Each one has a certain chance to get you a certain prize. You can only flip any one of them 100 times in total. There is a solution: reinforced learning. Reinforcement learning is a fascinating branch of artificial intelligence that mimics the way humans learn through trial and error. It involves training an agent to make decisions based on a reward system, where the agent learns to maximize its reward by interacting with its environment. In this case, our environment is the slot machines. First, we need to set up a function for the agent to interact with the environment. Let's create a function that has three actions: 0, 1, 2 for the three slot machines. Different slot machines have different percentage of giving out the reward. 50%, 60%, and how about 90%? Using a function from NumPy, we can use the percentage from the actions to give rewards accordingly. So let's test it. Action 0 should give a reward of 10 50% of times. Action 2 should give a reward of 10 90% of time. It starts with no prior knowledge of the machine's payouts, patterns, or probabilities, so it will create two lists of a Q and N, initializing with 0. Q stands for how useful a given action is in achieving future rewards, and N is the number of times the action was chosen. Ellipsin is the percentage that the agent will explore, meaning choosing a random action, and the rest of the time it will choose the action with the biggest Q value. Num steps means how much times it will play the slot machine. 1,000 times, so the results will be more consistent. As the agent receives feedback in the form of rewards, it will start to refine his strategy through a process called exploitation. The agent gradually selects actions that have been proven to be more rewarding in the past. Let's output the Q every time to see how it changes, and use the epsilon value to do the exploration vs exploitation. Update the action count, use the equation to recalculate Q. After the 1,000 tries are over, let's get the biggest Q, which is the most optimal action, and print out the action and see if it matches what our probability was. Let's give it a test run. As you can see, the Q values start at 0, increases over time to fit the expectations. For example, the 90% one returns around 9, which is around correct, and the others return around like 5 and 6, which is their expected Q value, and it outputs the best action, which is 2, which is 90%, so it is correct. Yay. Code is in the description, and have a good one.